Good day, this is part 2 of module 5. Let's look at the perceptrons. So this is one of the simple artificial neural networks. In part 1 of module 5, we have looked at McCulloch and Pitt's neuron, where we have to assign or determine the weights manually according to problem at hand. And here in perceptrons, we have a learning rule where we can apply this algorithm to adapt or to change adjust the weights automatically. So this is, as you know, developed by Frank Rosenblatt in 1958. Its learning rule is superior than Hebb learning rule, which we did not learn. It has been proven by Rosenblatt that the weights can converge on particular applications. And as we discussed earlier, this particular neural network or artificial neuron does not work on nonlinear applications as proven by Minsky and Peppert in 1969. By now you should know what is linear and nonlinear applications. And the activation function used here is the bipolar activation function with an arbitrary but fixed threshold. Recall, in McCulloch and Pitt's neuron, we used the binary activation function, where there were two possible outputs. Here in bipolar activation function, we have three possible outputs. And the weights are adjusted according to this perceptron learning rule. This is weight I at iteration t. I will explain later what is iteration, but for now you can accept this as new weight I equals to old weight I plus alpha. Alpha is learning rate multiply target or desired output multiply input I. So this is how the algorithm looks like. In step 0, we have to set up the neural network model which follows the problem to be solved. For example, if you have two inputs and one output, then you can imagine you have a circle with two or three lines coming in. I say three lines coming in because here we have additional bias input, where the input is always 1 and the weight is called bias, as we will see later. And the two other lines represent the inputs and one line coming out represent the output. So here we have to initialize weights and bias. For simplicity, we can set the weights and bias to 0 or randomize it. We have to set the learning rate alpha between 0 and 1 and threshold of our bipolar activation function between 0 and 1. And for simplicity, we can set the learning rate to be 1. So learning rate appears in the learning rule here. So if we set this number to be high, the learning or the adaptation will be fast, but we have a risk of jumping over the correct values of weight. On the other hand, if we set this value to be small, the learning or the adaptation will take a long time. So it's always a trade-off whether we have to set this high or low. It depends on the application and how we perform. So step 0, that was it. Step 1, while stopping condition is false, we have to do steps 2 to 6. For each training pair, that is for each row of our data, we have to set activations. You have to give the inputs, compute the summation of signals as we saw earlier, determine the output. So this is how the output of our bipolar activation function to be computed. Whenever S is greater or equal than our threshold, the output is 1. Whenever it's less than negative of the threshold, it's minus 1. Otherwise, it's 0. So you can imagine how the bipolar activation function would look like. If binary activation function looks like a step function, here it is slightly different. You should know how to plot this. So So that was step 4. You have to compute the response, right? This is the output of our neuron. If the predicted output is not equivalent to the target or the desired output, you have to adjust or adapt the weights using the formula I showed you earlier for both weights and the bias. So for the weights, I here refers to input 1 or input 2 or input 3. So new weight I equals to the old weight I plus alpha desired output multiply input. And in bias, it's similar except that we don't have xi because the input is always 1 here. However, if the predicted output is equivalent to the desired output, then no changes. So you maintain the weights and the bias. And when no weights changed in step 2, that means if for all your data the weights remain the same, which imply that predicted output is equivalent to the desired output, then you stop. You're done. So let's look at an exercise. So using the perceptron, solve the AND problem. This is an AND problem. In the table below, show the results of the weight adaptations until convergence. That means until you're done, until the weights don't change for each iteration. So whenever you do for each row, you have to supply the inputs. You have to compute the summation of signals, compute the output of the neuron, and you have to adapt the weights if needed. That is one iteration. Iteration 1, again, you have to do the same for iteration number 2, which means for the second row of the data, iteration number 3, iteration number 4. And you repeat back to iteration number 1 over and over again until you have convergence. Okay, so here some conditions are given. You have to use the bipolar activation function, which is common in perceptron. You have to initialize the weights to be -1, initialize the bias to be -1, set the learning rate to be 0.5, and set threshold to be 0.2. Threshold is concerned with our bipolar activation function. So you should be able to know how to do this, but because this is our first exercise, let's see how we can do this. So in step 0, as we have gone through earlier, it says that we have to set up our perceptron according to the problem. So this is our problem. As we can see, we have two inputs, x1, x2, and one desired output. So basically, you have to design a perceptron such that this will be the outputs when you fit in these inputs. Because you have two inputs, you have x1, w1, x2, weight 2, and you have a bias input as well, where the input is always 1. So your task now is to adjust these values, W1, W2, and the bias. And the initial values are given in the question. The initial values of W1, W2, and bias is -1. The learning rate, which means the alpha here, is given to be 0.5. Threshold, the cutoff value of or the threshold value of our bipolar activation function is given to be 0.2. And you should know from here, this is how our bipolar activation function looks like. S is given by this formula, which is the summation of signals that go into our neuron. And the output is the y-axis. So epoch 1. So epoch, in each epoch, we adjust the weights or we go through every training data. So epoch 1, we have iteration 1, which means we look at row number 1, iteration 2, we look at row number 2, 3, 4, where we look at row number 4. So in epoch 1, iteration 1, we start with row number 1, we have to compute the summation of signals S. So x1 W1 plus x2 W2, sorry, this is a mistake. Plus bias. So what is W1, W2 and bias? It is minus 1, minus 1, minus 1, because this is the value that we have initialized when we set up our perceptron. So minus 1 multiply minus 1 plus minus 1 multiply minus 1 plus bias minus 1. So 1 plus 1, 2 minus 1 is 1. So S is 1. So if you have S to be 1 here, you know output is 1. But this is not equivalent to our desired output, minus 1. So we have to adjust the weights according to the learning rule, this formula. So the formula is new weight equals to old weight. Old weight is minus 1. We're talking about W1 here, plus alpha 0.5 given in the question, multiply target minus 1, multiply input 1 minus 1. So minus 1 plus 0.5 is minus 0.5. We have this value. For W2, again, old W2 plus alpha target multiply x2. x2 is minus 1. So again, we have minus 0.5. For bias, old bias, which is minus 1 plus alpha multiply target. So minus 1 minus 0.5 is minus 1.5. So we have completed our iteration 1, and this is our new weights and bias values. Next, iteration 2. We are looking at row number 2, where x1 is minus 1, x2 is 1. So minus 1 multiply W1, which is minus 0.5, plus 1 multiply W2 minus 0.5 minus 1.5, the bias. So 0.5 minus 0.50 minus 1.5 is minus 1.5. If we refer to our bipolar activation function, whenever S is minus 0.5, the output is minus 1. So minus 1. So fortunately, this is equivalent to our desired output. So no adaptation is needed. It remains the same. W1 remains as before, W2 remains as before, and bias remains as before. Now, iteration number 3. We're looking at row number 3. So what is S? S is x1 multiply W1. This is W1. x2 multiply W2 minus 1.5. So minus 0.5 plus 0.5 is 0, minus 1.5 is minus 1.5. And this value, after going through our activation function, it becomes the output is minus 1, which is equivalent to the desired output. Again, no changes in the weight and bias values. So W1 remains as before, W2 remains as before, and bias is the same as before. Iteration number 4 now, we look at the last row. Again, S is 1 multiply W1 plus 1 multiply W2, which is minus 1 minus bias. It's minus 1.5. Minus 1, negative 1 minus 1.5 is minus or negative 2.5. and the output of our activation function will be -1. However, our desired output is 1, so it's not equivalent to our desired output. Therefore, we have to apply the learning rule, or we have to adapt the weights. So all weight plus alpha target input 1, the value is 0, W2, all weight, this is all weight, previous weight, plus alpha target input 2, again it's 0, bias is all bias plus alpha target, this is -1. So now our weights are 0, 0 and our bias is -1. So we are completed with epoch 1 because we have gone through all of our data. So as you can see, the weights are keep on changing. The weights are not consistent throughout the epoch. So we are not done yet. We say the weights and bias values have not converged. So we have to continue with epoch number 2, and we have to start with iteration number 1. So -1 plus weight 1. What is weight 1 now? Weight 1 is 0, right, from before. So not this one. You don't look at this one. We are here. We are computing W1, but we are using the previous weight because we have not computed the new weights and bias for iteration number 1 here. We are here. We have to refer to this. So -1 multiply 0, -1 multiply 0 is 0, minus bias is -1. The output from our activation function is -1. It is equivalent to our target. You don't have to adapt the weights. So we remain 0, 0, -1. Iteration number 2, -1 multiply 0 plus 1 multiply 0, which is 0, -1. The answer is -1. The output is -1, equivalent to our desired output. No changes. 0, 0, -1. So this is our latest weight and bias values. Now iteration number 3. 1 multiply 0 plus -1 multiply 0 is 0, minus the bias, S is -1, output is -1, equivalent to the target. Again, no adaptation. 0, 0, -1. Iteration number 4. 1 multiply 0 plus 1 multiply 0, it's 0, -1, we have -1. Output is -1, is not equivalent to our target because our target is 1, therefore we have to adapt the weights. All weight, this is all weight plus alpha 0.5 plus target multiply x1, we have 0.5, this is 0.5. New W2 equals to old W2, this is old W2 plus alpha target multiply input 2, 0.5, we have 0.5, and bias is old bias plus alpha target. So -1 plus 0.5 is -0.5. So again, if you see over one epoch, starting from here to here, we can see that the weights changed here. It's not consistently the same. So the weights and bias values have not converged. We are not done. We have to repeat with epoch number 3. So epoch 3, we do the same. I'm not going to go through line by line because by now you know what is S, what is predicted output, how do we adjust the weights and so on. So let's glance through. As we can see, we are here, we are computing this one, but we have to refer to the old weights in order to compute our S. Our S is -1.5, output is -1, equivalent to our target, no adaptation. These values we update here: 0.5, 0.5, minus 0.5. Second iteration, S is minus 0.5, output is minus 1, which is equivalent to our target. Again, no adaptation, so we update here: 0.5, 0.5, minus 0.5. Iteration number 3, S is minus 0.5, predicted output is minus 1, equivalent to our target, therefore no adaptation. We update here: 0.5, 0.5, minus 0.5. Iteration number 4, S is 0.5, predicted output is 1, which is equivalent to our target or desired output. Again, no adaptation: 0.5, 0.5, minus 0.5. If we look at over one epoch, we can see the weights don't change at all, the weights and bias values. So we have achieved convergence, or we say the weights and bias values have converged. So we can stop adjusting the weights because we are done. So now if you take this value 0.5, 0.5 and minus 0.5, W1 is 0.5, W2 is 0.5 and bias is minus 0.5. And if you apply these inputs, you would get the desired output here. So for example, if you apply minus 1 and minus 1, you would get minus 1 here. If you apply the last one, you would get the output to be 1 here. So we say that we are done with the training and we can use this network for real application. So now what if you have slightly disturbed inputs or noisy inputs? What if you have inputs to be 1.1 and 0.9 here? What is the expected output? Because you have to know these inputs are perturbed by noise. It should be 1, but somehow you have input to be 1.1 and x2 to be 0.9. You should expect the output to be 1. But the question is, does Perceptron give you 1? So please try that as a homework or as an exercise.